In this video, we're going to continue looking at these series of sequence and series, well, infinite series convergence tests. So we've done this column a couple videos ago, this column last video, and we're now down to this last column here. So if you haven't done these, you might want to pause this, work through these 5 problems before we go further. So I'm going to assume you've done that. We're going to run on to number M, letter M here. Okay, so we're summing from k equals 0 to infinity of 3 to the k times k plus 1 over 7 times k factorial. Remember, 0 factorial is 1, so we're not dividing by 0. In fact, this is always a positive thing. The factorials and the exponential there, but especially the factorials, are a giveaway that the ratio test is a good thing to try. So let's do that. We take the k plus 1 term divided by the kth term. So you take the thing basically as it is, put in the denominator, replace, same thing, but replace the k's with k plus 1 there, in the top. So you invert and multiply here, write as one fraction, everything's positive, so we can drop the absolute value. So this is 3 to the k plus 1, this is k plus 2, 7 and a k plus 1 factorial in the denominator. There it is. And here I put the 7k factorial in the top. And then the 3 to the k plus 1 here. Now notice 7k factorial means k, then factorial, then times 7. Factorials take precedence over multiplication in the order of operations. So let's see what we got here. The 3's are going to cancel here. 3 to the k actually cancels, leaving a 3 in the numerator. And that should have been gone in the denominator at that point. Oh, never mind. I just rewrote it as 3 to the k plus 1 is 3 times 3 to the k. Now they cancel, leaving just a 3 in the top. Let's see what else we've got here. K plus 1 factorial is k plus 1 times k factorial, so those k factorials are going to cancel. There was a 7 both places, so that just cancels out. And let's see what's left. Well, let's see. There's a 3 left. That's gone. K plus 2's left. Those 2 are gone. That's gone. That's left. K plus 1. That's gone. There's another k plus 1. That's still there. That's gone. So you got a k plus 1 squared in the denominator. I multiply by 1 over k squared. Distribute here, we get 1 over k plus 2 over k squared. Denominator, I get a square on the outside, then distribute the 1 over k. I get 1 plus 1 over k. Take the limit as k goes to infinity. The bottom goes to 1. The top goes to 0. So the whole thing goes to 0, which is certainly less than 1. So the series converges absolutely by the ratio test. The directions say to approximate this as well with a sum of the first 50 terms. And it looks like I summed it from 1 to 50, not from 0 to 50. So let me redo that. Okay. Just clear this out. All right, so we go to the sum, and I should be going from k equals 0 to 50. Actually, I think the direction said sum it from 1 to 50, but this one actually starts at 0. So I'll go from 0 to 50. 3 to the k times k plus 1. So let's put a fraction in there. A 3 to the power k. And get out of the power, parentheses k plus 1. And the denominator is 7k factorial. 7 times k factorial. I could get the factorial probably in here. I could from from some symbols here. There it is. I can also just type it on my computer, my screen. 7k factorial. I'll just do it that way. Oh, I had I was in the wrong place. That's why. All right, and well, there's an exact value. Let's just take that and do approximate value. So let's use that instead of this. And let's make it a little smaller. Let's do this. And change this number to match 11.4774496,704. Of course, that's just an approximation of the infinite sum, which we don't know exactly what that is, but we can approximate it with the first, well, this is actually 51 terms. All right, the next one. Sum from k equals 1 to infinity of 1 plus sine square of k over k, 8 the square root of k. Everything's positive here. The numerator might be going up and down some, but sine square of k, well, sine of k is always between -1 and 1, so sine square of k is always between 0 and 1. So the top is at least between 1 and 2. And the denominator starts at 8 and keeps increasing. So eventually this thing is going to, well, it may be going up and down a little bit actually, but it's probably going to be decreasing at some point. It's going to approach 0 by the squeeze theorem, so divergence test is not going to help us. But we can compare it to 1 over the square root of k, which is k to the -1/2. We'll do 1/8 of that. Okay. And so this actually turns out to be bigger than that. Sine square of k is adding at least some positive amount to that. And so that fraction is bigger than 1 over 8 square root of k, which is 1/8 k to the -1/2. That sum is 1/8 times the sum of that p series, which is divergent. That goes to infinity, and this is something at least as big, so it also diverges to infinity as well. So that was a direct comparison test. This next one, the sum from k equals 1 to infinity of 4 k to the k over 3 to the k, k factorial. Those powers there of k, and especially that factorial, tells us that a ratio test is a good chance that we should use it. So here it is. A sub k plus 1 over a sub k, absolute value, take the limit as k goes to infinity. So there's the original, 4k to the k over 3 to the k, k factorial. Same thing here with all the k's replaced by k plus 1, both the base and the power there, just the power here, and but for the factorial there. Now, flip and invert and multiply this bottom one, so this denominator goes to the top, that denominator goes to the bottom. So here we are, let's see, we got a 4 and a k plus 1 to the power k plus 1. In the top, we got the 3k to the 3 to the k plus 1 and the k plus 1 factorial on the bottom. Here we have the 4k to the k in the bottom and the 3 to the k, k factorial on the top. Okay. 3 to the k plus 1 is 3 times 3 to the k. K plus 1 factorial is k plus 1 times k factorial. All right, so let's see what happens here. The k factorials cancel, the 4's cancel. That k plus 1 and that k plus 1 cancel. So we're left with the other k plus 1 to the k. See, k plus 1 to the k plus 1 is k plus 1 times k plus 1 to the k. All right, and the 3 of the k's cancel. So let's see what happened. That's gone. That is still there, k to the k. That 3 is still there. These 3's are gone. That k plus 1 is gone. That's gone. This k plus 1 to the k is still left. Okay. So I can bring the 1/3 out front. And then I've got k plus 1 over k to the k power. And this is distributing. This is 1 plus 1 over k to the k power. That is exactly the definition of E. So that's E divided by 3, which is less than 1. Remember, E is a little less than 3. It's about 2.72 something. So that's a little less than 1. And when you get a limit less than 1 on this right here, on that ratio of terms, ratio test tells us that series converges absolutely. So this series converges absolutely by the ratio test. So if we sum up the first 50 terms here, which I did with the TI Inspire calculator, we get this. You could also do this on a TI-84 as well. The next one is summing from k equals 1 to infinity of k squared e to the minus k squared. So if the power out front were just k to the first power, we could probably use the well, if it was just one less power than the power up here, we would have been able to do a substitution and do an integral test. But as it is, that's not going to be a good option for us here. So we're going to use the ratio test. Okay. So put in the original here, put in the same thing with the k plus 1 on the top, absolute value, take the limit as k goes to infinity. Okay, so let's see what we've got here. I kind of split this into two factors. The k plus 1 squared over k squared is k plus 1 over k squared. And then here, I'm just working this out. So I work this out here. K plus 1 squared is k squared plus 2k plus 1. Then you got the opposite of that, distributes is minus k squared minus 2k minus 1. Now I can subtract exponents here. The k squared parts go away. So I get e to the negative 2k plus 1. Well, if these two limits exist, then we get there. Well, this limit, this first one, goes to 1. When you distribute the k here, you get 1 plus 1 over k. The 1 over k part goes to 0, so this is 1 plus 0 is 1, squared is 1. But this e to its negative power, as the power gets, basically approaches negative infinity, that whole thing approaches 0. 1 times 0, of course, is 0. So this approaches 0. That's, again, less than 1. So that converges absolutely by the ratio test. We can approximate with adding up the first 50 terms, which I did here on a calculator, to get about 0.44. Here we have the sum equals from k equals 1 to infinity of negative 1 to the k, the fifth root of x to the fifth plus 4k over 3k squared plus 5k minus 7. Looks kind of complicated, but first of all, we've got an alternating here. So this might be an alternating series. Well, it is an alternating series, and the alternating series test might work for us. We take if we ignore everything but the biggest power term, we get rid of that. We got the fifth root of k. The fifth is just k. And if you ignore everything but the first one here, you get a k over k squared. So that's 1 over k. So it should behave somewhat like the alternating harmonic series. So we suspect it'll converge, but do it conditionally. So if we look at the absolute value of it here and do a limit comparison test to 1 over k, we're going to find that it diverges. Okay, and so it doesn't converge absolutely. So to work out the details here, this k comes to the top here. Then what I ended up doing is multiply top and bottom by the 1 over the fifth root of k to the fifth, which is, and then a 1 over k, so it's 1 over k squared. So I did that at the bottom. So distributing the bottom, that's 3 plus 5 over k minus 7 over k squared. And the top, the 1 over k and that k canceled. And the fifth root here is there. And then I distribute the 1 over k to the fifth. So that's 1 plus 4 over k to the fourth. Okay. This part goes to 0. Plus 1 is 1. Fifth root of that is 1. So the top goes to 1. And the bottom's going to 3. So that goes to 1/3. That's something in the interval from 0 to infinity, including infinity, since this one goes to this one diverges. Infinity would have been a result that would have been acceptable to show that this diverges. So this diverges. Now this, though, is not what we started with. This is the absolute value of what we started with. So this says it does not converge absolutely. Okay, however, it does alternating sign. The limit of the absolute value of the integrated terms is 0, okay, which we can see by just looking at this, okay? So looking at this here, we multiply by 1 over k squared again. Here I'm going to think of k squared as the 5th root of k to the 10th at the top. So this is 1 over k to the 5th, 4 over k to the 9th. That's all going to go to 0. And then this is going to go to 3 in the bottom. So this is 0 over 3. That's 0. So the limit is 0. Okay, so that's good. And then if we just knew that the terms were positive and decreasing, alternating a sign and decreasing. It's clear that they're alternating sign. The k to the 5th plus 4k and all this stuff in the bottom is all positive. Let's see, even when k is 1, the stuff in the bottom is positive. Okay. And then that negative 1 to the k says we got an alternating sign. Now we need to show that the individual terms are decreasing. That's a little harder to see, but we're going to do it with a derivative. So I'm going to change the k's to x's here and do the derivative using the quotient rule. Think of that as a power function at the top. So bottom times derivative of the top minus top times derivative of the bottom over the bottom square. This derivative here is like u to the 1/5. So it's 1/5 u to the negative 4/5. Derivative of the inside is 5x to the 4th plus 4. Derivative inside here is 6x plus 5. They both, and of course you got the denominator squared. They both have this x to the 5th plus 4 to the x to a power. We factor out the smaller of those two powers, which is that to the negative 4/5, which I wrote in the bottom. Dividing that, we get, let's see here. Yeah, so I multiply, or another way to say it is multiply top and bottom by x to the 5th plus 4x to the negative to the positive 4/5. That puts it in the bottom, and the top we distribute, so it's going to cancel that out. So that leaves this trinomial times that binomial. I'm also going to multiply top and bottom by 5, so it's going to cancel that out. That puts a 5 in the bottom. Now here I need to multiply by 5 and by this to the 4/5 here. Well, you add the powers, that's 1, so this becomes the first power here. All right, now we just got a lot of stuff to look at. So what did I do next? Looks like I just copied exactly the same thing again. No need for that. So now I multiply all this out and all this stuff out, combine like terms, and we end up with a negative here. All the terms turn out to be negative whenever I put them together here. So I factor the negative out. Now everything else at the top is positive. So that's a negative. That's a positive on the top, positive on the bottom, negative out front. That's a negative. So this is a decreasing function. So that was perhaps the hardest part. So we have to show the function's decreasing, so that the limit of terms is 0 and alternates in sign. Then that's going to converge. But we saw that its absolute value diverges, so it converges conditionally. So it converges conditionally by the alternating series test. Okay, so at this point you should be pretty good at working out these different series tests. Practice this on homework till you get really good at it, and then we're going to go on to applying this in a little bit to some different kinds of things. We're going to start talking about Taylor polynomials, powers, and power series in the next few videos.